All right, so this is section, was it 40, right? So PySpark, basically big data stuff. So let me just ask you guys, has everyone got to this section, or have you guys just started it, completely done with it, or like I haven't looked at it yet?
Done with it.
Cool.
Yep, same.
Okay, cool. So you guys all got a feel for already what's in there. So I will be upfront with you guys. There's probably so much more in Spark that there to do. Like, it's kind of funny, to be honest, being one section is kind of a little, I don't know how to say it, but like there's so much more we can talk about for like data. Like really we're talking about data engineering. Basically, how do you process this data, large amounts of data? So know that I'm going to go through a lot more conceptual stuff. And so I'll explain like where you would apply this. Spark isn't the only one you can use. PySpark is connecting to Spark, but Spark is one of the newest ones. It used to be Hadoop, which was kind of a big player for a long time. It still is, but it tends to be considered a little old school, newer, and stuff like that. So I'm going to start sharing my screen. And I usually just share my one little window, everything. Is this it? Yeah. Always have PowerTime. Okay, and then all my windows go away, and I can't find you guys. All right, there you are. All right, so I have a few things we're gonna go over. So one thing to note, I usually share this with my students, is I have a repo. I just keep it for like all my different cohorts. So I'll share this in the chat now, and I'll make sure to share it out on Slack. I think it's not up to date right now, but the stuff I'm going to talk about, those will be living in basically this big data PySpark area. Yeah, it's not up to date, so I need to push my changes. But this is where you can find the notebooks I'm going to show you today. That way you can kind of play around with it or reference it again if you want. Okay. So let's get right into it. So let's check out big data. So what is big data? So you guys have read this section a little bit. How would you guys describe big data?
Same as regular data, just a whole lot more of it.
All right, whole lot of data, right? Data is just a lot of it, right? Any other definitions we can use besides just being lots of data?
It's generally a lot more, what was it, high volume, high velocity. There's one more V, I can't remember what it is.
Yeah, so there's the 3 V's, right? You got the big ones that usually think of: high volume, high velocity. Okay, we'll talk about what that means. Basically, a lot of incoming data. And the last one is variety, which is a little subtle. Like, why is variety kind of a big part of big data? We'll talk about why that is. This is kind of what separates like what big data is and why we need to approach it in a different way. A lot of times I've heard people say like, oh, big data is just a bunch of data. It's like, it's not that much different. Like, I've literally heard like other people like analytics say this, and I'm like, oh, you haven't delved into like what big data really looks like. Because basically it comes down to the fact that you can't process it all on your one machine. And those parts of high volume, that seems pretty obvious. If there's a lot of data, you can't put it all on one machine. The velocity is a little more subtle, but hopefully that kind of makes sense. Like, oh, it's coming in a lot faster. So you have a lot more data coming in. And then the last one, variety, is probably the most subtle one. It's like, why would variety mean that we'd have to consider, like, why would we have to use a distributed system to use? I'm using words here that hopefully you guys already went through, but we'll talk about if you aren't familiar. But why would variety be like something that we'd have to worry about for big data?
Because you can just run like one operation on a large set of data, because like you said, like if there's variety, then you have to be careful how you're like you can pick out certain things to actually like run some transformation on.
Right, and that's exactly right. The variety basically adds an extra complexity where we have to kind of consider it through. So oops, let me expand this out. So really what we talk about is basically it's a different kind of thing. It's basically got a lot of different stuff. There isn't a really clear like this is big data, this isn't big data. It's kind of like the similar like when does a heap become a heap, or when is what is it like when a pile becomes into a heap? It's like how much stuff did you put in a pile until it becomes like a heap? It's kind of like there's not a clear distinction, but usually people kind of say like, oh, you know it when you see it kind of deal. But for generally, we'll talk about like things like how do we identify this, the 3 V's of data. So I'm actually going to skip over this part and actually talk about the 3 V's. So like we said, volume, velocity, variety, right? volume meaning large amounts, and large amounts mean that you can't fit it all in one computer's memory. Right now, we've been using Pandas for a long time. Pandas is great. Jupyter Notebook is great to process data and test things out within one machine. And one machine can be very powerful. A lot of data science, machine learning stuff, it's 128 gigabytes of RAM. That's pretty typical that I see. And that means that you can fit in all of that data into 128 gigabytes. Pandas loads it all into memory. There's some kind of subtle stuff you can do like called chunking, where you can kind of split up the data into different parts. But for the most part, basically all the data you have is loaded into your machine. Well, obviously, if you have huge amounts of data, you're not going to be able to fit it on your machine all at once. That's an issue. Other part, velocity, right? Quickly generated, it's going through very quickly. It doesn't make sense for you to like have one machine trying to get all this data in. If you think of like just all the number like of YouTube, like, I mean, YouTube has, I remember at one point, it's completely wrong probably now, it's like 40 hours of video per minute, I think. Like that was stated like at least a few years ago that I can recall. I'm sure it's even more now. So you can imagine how much is being uploaded into YouTube constantly, and having one machine deal with that is just not going to happen. It's not going to be able to work quickly enough. It's going to basically clog up its system. Variety is kind of the most subtle one. It's unstructured. And so this is actually a big part of like, you'll hear people talk about data warehouses. Has anyone heard that term before? Data warehouse? Yeah, so data warehouses are kind of like, again, like quote unquote old school. It's not that it's bad or anything, but it's just kind of like what you hear a lot of. Data warehouses are basically structured data. It's data, it can be very large amounts of data, but it's structured in a certain way. You're able to parse through it. There's certain like, cloud systems you can use to actually process this. We now have this term called a data lake. Have you guys heard that? I think that's actually in the curriculum talking about. Okay, so a data lake is kind of like a data warehouse, but you can kind of get like maybe a little bit of terms. Data warehouse, you can imagine like if you've ever been in a warehouse, it's very structured well. There's logistics of like where things are ordered. Data lake is kind of just like, oh, data, just throw it in there. And that's kind of like what a data lake is. And so we won't use like tabular data as much. It'll be like, sometimes there's images, sometimes there's pictures, sometimes there's, text, sometimes there's different formatted text. It's just a big lake of data. And that's kind of like the description of there. And so that's what all this together, large amounts of data coming in very quickly. There's a huge mess. That's why we have to consider this new kind of thing, which is basically how to process data. Okay. Now, as you kind of read through the curriculum, basically the way we do this is through distributed and parallel systems. So before we even talk about these kind of systems, there's these things, I think you could probably like search for this and you could see like the original lecture, but it's the numbers everyone should know. And basically this will help you determine for your big data, whether it's big data, and also what kind of things you have to consider for your big data. So these are like the basics, and like this is more computer sciencey, but it becomes relevant for us actually talking about it in data science. So the first part basically is our CPU. That's kind of like the brain of the operation. So if you're familiar with your computers, right, that's essentially the one doing all the calculations and stuff like that. The memory is our kind of like our memory, or RAM is our short-term memory. So like I said, like, might have like 64 gigabytes to 128 gigabytes on a normal, data science processing in single machine. And basically you can think of like how much it can store in that memory for a second. And then storage, like our SSD, HDs. SSDs are becoming more and more common for like servers and stuff like this. So you actually see a lot more of faster processing. This is kind of like your long-term memory. You can think of it like your brain, right? It's like, this is a long-term memory that's stored far away that you have to think for a second, like, yeah, that's right. And eventually it kind of comes out. Versus short-term, basically, it's kind of like the things that were just said. So that goes away very quickly. And then of course our network, which is kind of like the connection between all of these different parts. So in order to get all the information here, basically it's kind of a hierarchy. CPU is kind of like the quickest, at like about like 5 nanoseconds right now. Sorry, not 5 nanoseconds, half a nanosecond, depending on your CPU. And basically it's processing all that data very, very, very quickly. Your memory right here, okay, which is their second fastest, about 100 nanoseconds, okay, is basically pulling this data in there and giving it to the CPU, and then the CPU gives back data to the memory, and it does something with that. So it's either store it away or send it off on the network. Okay. Note that this is like really slow compared to the CPU. CPU is just like going like crazy. RAM is still very fast compared to the other parts, but it's still relatively slow compared to the CPU itself. And that's partly because of the actual structure of how CPUs work. Okay. And then we have our storage, our SSDs, our HDs, which basically if your memory's in your RAM, it's going very, very quickly. SSD, you basically, and even HD, a hard drive, right, which is like the spinning disk, like you imagine like little I don't know if you ever opened up a hard drive and like seen what it looks like. I think I have one. No, I don't have one next to me. I put those away because they're just hanging around. But anyway, an HD, basically you have to have this spinning disk, and basically there's a little magnetic head. And basically every time you say, oh, find me this file, it knows where that file is, but it's got to physically turn that disk and find it. SSDs are solid state drives. There's not any moving parts, but it still has to do the same thing where it's like goes to its little flash memory and says, hey, where is this file stored? And it says, oh, it's stored over here. And then basically it can grab it from there. But because it has to say, where is it? It basically takes more time. So it's long-term. It's basically 15 times slower than memory. These are approximate numbers. You can see like these numbers don't quite match up. So it depends exactly what kind of SSD or like what kind of long-term storage we're talking about versus RAM. But it's like, it's definitely slower on the order of between 10 to even 100 times slower than our actual RAM, okay? And then the last part is our network. So our network is like, if you're getting data from like another server or from anyone like, you know, being uploaded to you, that's going to be your slowest bottleneck. It's going to take a long time, 150 milliseconds, which sounds pretty fast, but if you think about how quickly data can come in, it can take a long time. And these 4 different numbers really determine about how you approach your big data part. Again, this was originally come from Jeff Dean and Peter Norvig. Okay, so I think they're, okay, I did actually link it here. So there's actually a little blog here that talks about these numbers. These numbers will change over time. They've changed already. So just know that these numbers will change, but for generally, these will always be true. CPU will be the fastest, memory the next, like RAM, then storage, and then your network. And so one thing to kind of consider is about what kind of system you have, what kind of data you have, and how you should approach it. So we'll actually look at how, like how we do this in distributed systems, but it kind of give you a brief kind of thing of like how like basically how this like process works. I'm gonna draw a little diagram here. So you imagine like your CPU, which is your brain, and I'll try not to write the whole thing because it's gonna take me a long time to draw out perfectly. But you imagine then your data over here, and we'll ignore network, but you can imagine like the network coming in over here. And this is like your storage. So I'll put like SSD. And then this is like your RAM. Okay. So what happens with this is that basically, and I'm going to make my data this nice blue thing. And so basically what happens, we have some data. You're like, okay, cool. Like here's some data here. CPU says, hey, go ahead and grab this, send it off to RAM so I can process it. And basically this data gets sent over into this RAM part. So it's like, okay, like I'm going to read this whole file. For example, you might read 8 gigabytes of stuff into memory, into your RAM memory. If your RAM can take it, you know, it's fine. If it doesn't, that's when your computer kind of slows down and it kind of stops working. But we'll assume that it can do fine. Once it has that in the RAM, basically the CPU takes that data and then does all the number crunching. It says, oh, okay, let's map this out. Let's, you know, count out how many words are in here. Let's do the operations. Let's do a for loop. That's where all this stuff happens in here. And this happens very, very quickly. And then it passes off to RAM. And then it passes off to SSD. The problem is that when we actually try to do this stuff, SSD, like for the CPU, we're going to be like picture of our CPU. This data comes from off the SSD. It's like going in slow motion, like molasses. So it takes a long time for this data to be loaded completely off of here, over here, and the CPUs are like, all right, come on. Finally gets into the RAM, and says, all right, cool, pass it. Like CPU's like, give it to me, give it, and RAM's like, okay, just hold on, chill. I'll get it to you. And it eventually goes through a little bit faster, but it still takes a long time. And then the CPU crunches away and passes off to RAM, okay? And this goes through. The problem is when basically your RAM is completely filled up, but your CPU is just hanging there. Basically, it's taking so long for this data to get passed over to RAM, passed back, stored. The CPU is just like waiting this whole time, basically not doing anything. And this is what we call thrashing. Basically, your CPU is like twiddling its thumb, just being like, come on, like I gotta get something to do. And you're just waiting for this overhead to go through. And this is what we don't want, right? This is what takes like the most operations. Like this is what we really care about. So if the CPU is doing nothing, basically nothing's really happening. So we want to actually remove this part. And this is where we can actually do distributed networks, parallel processing, and how we can kind of like approach this so the CPU is always working. We want our CPU working at 90%, 95% as much as possible. That way it's going through that data very, very quickly, okay? A couple things to kind of consider when we do this stuff. This is when our network comes in, is that when we do a distributed system, what we essentially will do, it's kind of like, I used to do this as I was a teacher and like in middle school, and all teachers like never realize this. Like you might have like a stack of like 200 papers, right? Or maybe even more. And you got to like, when kids turn it in, they never put it in alphabetical order, right? Which, I mean, just expected. They're just going to throw the paper in, right? There's no way you're going to get alphabetical. But to put in the grading system, right, Usually it's alphabetic order, so you can do one of two things. You can do kind of like the annoying way, which is basically as you're going through it, you're like, okay, look at this part. Let me see this grade right here. All right, like, or what this name is. This name, look for it, look for it, look for it, look for it. Okay, put it in there, move on to the next paper, do the same thing. That takes a long time. So it'd be nice to have it all alphabetized already. So one thing you can do is, and this is what I kind of did a lot, you can use basically a search algorithm to order your papers. This is how I ended up getting in computer science a lot. It's like, hey, let's just sort through this, and you can actually sort it very quickly. But it's even quicker if you can say, okay, well, I have a stack of 200 papers. Let me give it to, say, 4 different people, so 50 papers each, and go ahead and alphabetize each one of those things. And once those are all alphabetized, then I can combine them all together and alphabetize with on that. And there's basically a little like really simple algorithm you can do this. Basically, you compare each paper. If you're curious, it's called merge sort. It's a computer sciencey thing, but you can make this happen so you get each person can sort each part, and then once it's all sorted within their little pile, you can combine them all together. That's essentially what distributed systems, parallel systems are going to do. The other way you could do this is like the slower way, where I'm trying to make sure I get this right. So this obviously can be much quicker. If it takes me a lot of time to sort through 200 papers, if I can split this task into 4 parts, and each one of those can do a little bit faster for those 50 papers each, and then combine it, the combining part's really easy. It's simple. This won't work though if I have, let's say, 50 papers and I have 10 people to help me out. It would take me more time to get 2 papers, pass it off to each person, each classroom or whatever, whoever's helping me out. All right, here, take 2 of my papers, sort those 2 papers, which is going to take them no time, but like they sort them very quickly. And then I have to go back, collect each one. And then after I collect each one, look at that one, I have to physically walk over back to my classroom, sort those ones, put them together. That's very quick, but me actually going out there to process it, it's going to take a long time. And this is where actually, depending on like what your system is and what kind of data is, it might make sense like, well, you know what, let's not distribute this out. Let me just do this on a local computer and not worry about it. And that can help you determine if you need to use big data, basically PySpark, or you can say, you know what, we can use Pandas because it's basically medium data or small data. Okay, so that kind of leads us into our next part. But any questions on this general drawing or CPU memory storage network? All sound pretty good. Cool. Okay. So I like to add that in there because it's like, it sounds basic, but it definitely is something you should consider when you're actually processing your data. So let's talk about distributed parts. So there's a difference between parallel and distributed processes. So, oops. Oh, that's fine. Okay, that's fine. All right, so a distributed part, basically, this is our 2 different parts. This is directly from the curriculum. This essentially is more of a server base where it's all connecting into one part versus a peer-to-peer network where they're each messaging each other. And so distributed, when we say distributed, what we really mean is that tasks are split up and executed by different workers. That's slightly different from parallel. It just means that the task is split up and put into different people to do different things. So basically, multiple CPUs each have their own memory. So you can think of it like their own computer, its own CPU, its own memory, and it has its own data to work with. And then once it works with that data, it will basically share that information through the network, basically through like messages of saying, oh, here, I'm all done. And so you can share this information back and forth, either with each other or possibly just with one big network right here. And the point is that you are distributing it, you're making it all separate stuff. Versus something that's sequential. Sequential is usually where one computer has to do one task, the next thing, 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 and then you're done. Okay. If you can split up those tasks into different parts, okay, that's when we get into parallel systems. And so when we do a parallel system, basically you're executing those parts in non-sequential order. And so again, the curriculum has a good example. This is traditional sequential where we have multiple steps that we have to do. And so we have to do step 2, step 3, step 4, and then we pass it off to another computer, right? Basically. So I guess this is kind of, I don't really like this description, but that's okay. Basically, we have these multiple steps versus parallel processing. We can say, okay, each CPU, each thread on the CPU, basically each like task, sometimes we'll call them like workers, is that each worker will have these set of tasks going through and do each individual part and then combine it off to the side. So note that this doesn't have to be distributed. This could actually be parallel processing, can be done on an individual computer. It doesn't have to be distributed where you have basically connection between the two. But usually when we're talking about big data, we're talking about a mix between parallel processing and this distributed network. Okay. And Any questions on like the difference between these two parts, parallel versus distributed? Cool. Thumbs up if we're still hanging out with me. Still looking good? Okay, cool. So this brings us into our different little tools, right? So, is this what I want to do first? Yeah, we're going to do this first. So our first thing we're going to talk about is a little bit of different tools that are used. And one of the reasons why I'm going to bunch this stuff too is that you will, as a data scientist, you might be working with one single team, which has a very specific way of using tools. You might not, each team does different stuff in how they approach things. There's no like, oh, everyone does this one thing. And the important part is actually understanding how distributed works, how parallel processing works, the concepts, and then being able to apply those to a specific tool set. Right now, for example, Spark is kind of like a big part in here, but I guarantee things might get improved in there. Also, Hadoop, which is, if you ever see like the little funky elephant, that's the logo for Hadoop. It's kind of an interesting story where that name come from. But anyway, Hadoop is more like old school. So more systems that kind of came online before, they used Hadoop, which is a Java framework. Actually, Spark also is too, but we have like basically Python layers that can interact with those parts. But Hadoop is more old school. You won't see it as often with newer like companies and new like, anyone who's doing new data processing. You might, depending on what their history is. But note that there's a lot of really great businesses that still use Hadoop. I think, for example, Facebook still uses Hadoop, not Spark, because it makes more sense. Like it's going to take them so much more time to transfer over into Spark that it's not worth their time. But there are some slight differences and advantages. And usually Spark is kind of like the go-to. It's kind of like the new kid on the block. It won't be the new kid. It won't be the best one out there. Who knows what's going to come up next, but these are constantly changing. And also, I like to say is that when you look at all the different tools for data, they sound like, they kind of sound like a Dr. Seuss book. Like it's kind of ridiculous. So just kind of like you hear things like Hive and Pig and like, Hadoop and Spark, and it cracks me up a little bit. But anyway, so let's talk about Hadoop. So Hadoop is probably the most like established one that's good for data, big data. It came about because of big data. It tends to be slower in general because it has to write to disk each time, versus in Spark, we'll see that Spark actually runs it all within memory. Basically, remember how, what's it called? When I say disk, I mean like your SSD, your HDD. Spark basically allows you to run it just directly in the memory, in the RAM itself. And that means it's a little bit faster because then you don't have to worry about writing it and then reading it and writing it and then reading it, where Hadoop does have to do this. But in some cases, it doesn't really matter, or it's about the same thing, or it's like the system's already in place and it works well enough where you don't need a huge amount of speed to do this stuff. So note that the storage, you'll see this terminology HDFS. Basically, that means Hadoop distributed file system. Okay, so that's kind of a common one you'll see. That's kind of like the storage itself. The data processing part is the Mapreduce. Mapreduce is kind of a weird one. It's not necessarily a programming language by itself. It's much more like a philosophy, just kind of like similar to how you guys learned about object-oriented programming. Object-oriented programming, it's not like there is object-oriented programming. It's a philosophy of programming. That's kind of like what Mapreduce is as well. Okay, and then there's actually a resource management layer. For example, I think it's Hadoop Yarn is the most common one right now. Again, sounds like Dr. Seuss. Yarn, Hadoop, Spark. There's all these weird words. But that's kind of like what you'll see. And basically, those are the different parts of it. There's how do you store it, how do you process it, and how do you manage the resources. Okay. Any questions so far about this? Cool. All right. So then this brings up to Apache Spark. So Apache basically holds in memory. It's really fast because it can do this. It basically is processing it on there itself. It's built on top of Hadoop, or it can be built on top of Hadoop, but it's also usually done on S3 on AWS. AWS and Amazon Web Services. Are you guys familiar with at least that term, that service, AWS? You'll hear that quite a lot as cloud service. So there's AWS, there's Microsoft Azure, which is not as popular but still exists. And then there's Google Cloud Platform. AWS, as of right now, is pretty much the king of like this. In fact, I think Amazon like loses money every year, but like what makes up for it is AWS. So most of the web actually runs off AWS. And there's some really cool tools and stuff like that. And honestly, we could go like I said, like a whole nother month talking about just data engineering and how to interact with like cloud interface and stuff like this. But we're kind of going to say, well, we want to process and do some interesting things, okay? So like I said, Spark has kind of been like the new kid on the block. He's kind of like the best one going through. It's really great for ETL, extract, transform, load, right? It's also used a lot for ML, as you guys saw in the curriculum. There's an example of how to do ML, was it ML, or do ML with Spark. So it's really great for distributed systems. And again, it's pretty fast, but know that you'll come across Hadoop depending on the system. But for the most part, it's not too bad because you have a Python layer most. Okay. Now just know, just because you can do this doesn't mean you should. So like I said, in certain situations, it might make more sense to use just a single computer than a distributed network. You can do a lot of stuff directly with Pandas without ever having to worry about the cloud itself. This includes a lot of stuff like if you ever try to look at Kaggle, are you guys familiar with Kaggle, kaggle.com? Yeah. So if you ever look at Kaggle, a lot of times you don't necessarily need to use like these distributed systems. They're not large enough and coming in quickly enough. But if you do have a really strong enterprise that has, you know, big volume, high velocity, or high variety, those are things that you have to consider too. Basically, if those things are more important or like are going to affect the way you're going to work, you might have to do a distributed system. And this is where you kind of go into it. And again, cannot stress this enough, there is so much more to learn for data engineering itself. So just know that like we're kind of teaching you like the tip of the iceberg, but hopefully at this point you can start looking at stuff. Okay, so cool if I move on then? Sound pretty good? Okay, these are all like high conceptual stuff, so I just want to emphasize those parts.